Hello, this is Jack Jackson. Today we're going to be talking about power functions. So this material is probably best learned in a discovery type approach, and I have a Minds On Active Learning project called Exploring Power Functions that does just that. So you should stop this video now if you've not worked through that project, and I've also posted solutions to that, so you should basically learn most of this material from that project and its solutions, and then come back to this video for a hopefully fairly quick review. So we'll be talking about the definition of basic power functions, see what the structure of the formula basically is, and then we will look at different graph and table characteristics in the first quadrant, and then we'll talk about symmetries in which quadrants and some domain and range and other issues next, and then we'll summarize the different shapes we could get. So basic power function is just y equals x to the n power, f of x equals x to the n. And notice this is just a one operation function, one step. You just have a variable base and then you raise it to a constant power. For example, if n is 2, you're just squaring every input. So it's exactly one operation only. So again, we have a variable base and a constant power n. But it turns out that there are a variety of different shapes that we're going to get. We're going to turn out to get about 11 different basic shapes, depending on what the power of n is. So the shape can vary a bit, okay? And depending on the type of number n is and the size of n, we get these different shapes. But along the way, we're going to talk about various important ideas about graphs and about formulas and tables. In particular, we're going to talk about a lot of characteristics that graphs could have. We'll talk about properties of exponents. We'll talk about domain and range of functions. We'll talk about increasing, decreasing, or constant, relative extrema and endpoints, concavity and inflection points, continuity, discontinuity, hole in the graph even, a vertical and horizontal asymptote, and y-axis and origin symmetry. So all of these functions, all of these things show up in one or more of these functions depending on what n is. So a couple of general things. Notice that a positive to any power is positive, so all the graphs are going to be in quadrant 1 and none are going to be in quadrant 4. Some of the graphs, quadrant 1 is all there is, some are 1 and 2, some are 1 and 3, but none of them go into quadrant 4. 1 to any power is 1 for all numbers n, no exceptions, so the point 1, 1 is on all the graphs, and ultimately that's the only point that's going to be on all the graphs. 0 to the n is 0 for any positive n, so if n is positive, 0, 0 is on the graph, and if the n is a negative or 0, then it's actually undefined for input of 0. So let's start looking at the most basic ones, powers 1, 2, and 3. That second one should say x squared, and that is the dark blue one. And notice that I've just made a little table of certain key points here. And so notice if we start with, as we've said, they all go through 1, 1, and you see that's the point in common right here. And these, since the power is positive, also go through 0, 0. Notice that the red one, y equals x, is just a slanted line, a line with slope 1, and that's sort of it's called the identity function. It sort of does nothing if you think about it, because it just, the input equals the output. So the input comes in, nothing happens to it, it stays the same for the output. And of course, as we know from our earlier work, that is a straight line, so it's a continuous straight line. This is the only one that's going to be a continuous straight line. Now, if I put in a number bigger than 1, and square it, notice that I get a number bigger than what I get here than the input. So 2 times 2 is 4, which is bigger than the input of 2. So that means that when I get to 2, the dark blue graph is going to be above the red graph. See, it's at 2, 4 instead of down here at 2, 2. So it's above that graph. And then you get even further above the graph when we go over here to 3. 9 is even farther above 3 than 4 was above 2. So you get 3, 9 is up here on the dark blue graph, even further above the red line. In fact, it continues to move further and further away from that red line as we go further and further to the right. But look what happens between 0 and 1. If we put in 1/2 and square it, then it actually gets smaller. It gets to be 1/4. So that's below. So 1/2, comma 1/4 is right in here on this dark blue line. And 1/3, comma 1/9 is down here even further. So that's below. When we raise it to even higher power, x to the third power, then 2 to the third power is 8. So that's even higher up. So higher power, even higher up. And 3 to the third power is 27, even further up. That one's off this particular screen. So notice that the bigger the power, the bigger we get when we're to the right of 1, but between 0 and 1, it's reversed. So this light blue one's on the top, to the right of 1, they all equal at 1, and then it's below, between 0 and 1, and then they all equal each other again at 0, 0. And again, like I said, 1/3 cubed, 1/27, so that's below both the 1/9 and the 1/3, so it's both below the curve of the y equals x and the y equals x squared. So, if n equals 1, then we're talking about y equals x. That's increasing linear, goes through 0, 0, and 1, 1. If n is greater than 1, it's increasing concave up here in the first quadrant, and that goes through the point 0, 0, and 1, 1. Now, right now we're just focusing our attention on the first quadrant. They all have graphs in the first quadrant. Okay, let's add a few more to this. Now we're going to add to this x to the 1/2 and x to the 1/3. Well, look what happens here. Again, they go through 0, 0, and 1, 1 because they are positive powers. And again, they are still increasing. So all these positive powers gave us increasing functions. But whereas the powers bigger than 1 were concave up, power equals 1 was linear, power less than 1, between 0 and 1, was actually increasing but concave down. And notice we still have our result that the bigger the power, when you're to the right of 1, let's say here at 2, notice that the furthest down is on this kind of greenish one here when x is 1/3. Then the pink one, x is 1/2, or n is 1/2. N is 1/3 on the green one. N is 1/2 on the pink. N is 1 on the red. N is 2 on the dark blue, and N is 3 up here on the lighter blue. And so the bigger it is, the higher up we are for a particular x value, say at 2. Okay? If that x value is what? To the right of 1. If that x value is equal to 1 or equal to 0, then they're the same. And between 0 and 1, everything's exactly reversed. So you can see the concave down shape there for the powers between 0 and 1. What about a power of 0 or some negative powers? Well, x to the 0 is 1 everywhere except for 0 to the 0. So x to the 0 is this purple horizontal line right here, and it's a solid horizontal line except for a hole at 0, 0. So there's actually a hole in the graph at 0, 1 actually. Okay? So that one does not go through 0, 0. Also, the negative powers do not go through 0, 0. They do not cross the x or the y axes. Neither does y equals x to the 0. But whereas y equals x to 0 has a hole in the graph, these other two, for negative powers, x to the negative 1 and x to the negative 2, have vertical and horizontal asymptotes. If we notice, the bigger we let x get, the typo there, that should say 10, 10 there, and 2, 2, because it's just y equals x. And then this is okay, the ones down here are correct. So as we get x to be larger and larger, these last two with the negative powers get smaller and smaller y's. So they're approaching 0 as we go out to the right. So it looks like they're getting almost horizontal. They almost touch the x-axis, but not quite. They're always a little bit off, although they're getting closer and closer to it as we go further and further to the right. Similarly, as we come in with x's getting smaller and smaller, closer to 0, but still positive powers, positive x's, you get larger and larger y's, as you can see here in the table, and so that goes up and we have a vertical asymptote there. So, for x is greater than 1, the higher the power, the higher the graph. 1, 1, 1 is on all the graphs, but for x is between 0 and 1, the higher the power, the lower the graph. So they switch order. So notice we got n equals 2 on the bottom here, then n equals negative 2 on the bottom, then equals negative 1 is the darker red, n equals 0 is the purple coming up, then n equals 1/3, then equals a half, n equals, I forgot what fraction this was, but something between a half and 1. Then n equals 1 is the red one here. Then 9/7, 3/2, 2, 3. And so the power just, if you take a particular x like 2, where we can see all the graphs for all of them, you see that the higher the power, the farther up you are on the graph. Okay, if what? If you're to the right of 1. If you're at equals 1, they all go together. And then between 0 and 1, it's reversed. So the lower power is the highest. N equals negative 2 is the highest. Then negative 1, then 0, and then so forth. And they're exactly reversed between there. So we can summarize this based on the size of n. If n is bigger than 1, we've got increasing concave up in the first quadrant. It goes through 0, 0, 1, 1. If n equals 1, then it's increasing linear going through 0, 0, 1, 1. And if n is between 0 and 1, it's increasing concave down through 0, 0, and 1, 1. If n equals 0, we've got a constant line at y equals 1 with a hole in the graph at 0, 1, and it, of course, goes through 1, 1. If n is a negative number, so a negative power, the first quadrant, they all pretty much look kind of the same, decreasing concave up with a horizontal asymptote of the x-axis and a vertical asymptote of the y-axis, and again, they all go through 1, 1. Now, suppose we have a rational power, f of x equals x to the n, where n is a rational number of the form p over q, where p is an integer and q is a natural number. We can think of that as x to the p and then take the qth root of that. We're going to assume that the fraction is reduced, so the greatest common divisor of p and q is 1. And we've got 3 cases we're going to look at here. The first case is where both p and q are odd numbers. Well, we know what the first quadrant looks like. What happens when x is negative? Well, if you take a negative to an odd power, you get a negative, and then take an odd root of that negative, and you get a negative output. So negative n gives you negative out. That's third quadrant. And so it turns out this is going to be in quadrants 1 and 3. And notice specifically, if you plug in negative 1, you get an output of negative 1. Of course, an input of 1 always gives you an output of 1. So this goes through 1, 1, and negative 1, negative 1. In fact, in general, whatever you have in the first quadrant, if you'll rotate it 180 degrees about the origin, a half circle rotation about the origin, it will land on top of what's in the third quadrant. So this is what we call origin symmetry. Okay? Or another way to get there is to reflect over the y-axis and then reflect that over the x-axis, and that's going to land in the third quadrant. So this is origin symmetry is what we call rotational symmetry. So if we were just to take this and rotate it 180 degrees, like this, upside down, then you're going to see that the graph looks the same. So 180 degree rotation is going to be the same thing there. Okay? So that's called origin symmetry. And I've got several different ones graphed, like n equals negative 1 is the maroon, one of the maroon ones here, the one with the asymptotes, both in the first and the third quadrant. Both pieces together, so it's 2 separate pieces. The red one here, n equals negative 1/3 here, and also down here, 2 pieces there. The rest of them I've got are connected. If n is 7/9, y equals x is 7/9, it's coming up this way. It's actually concave up here, then it curves back around concave down. But it goes through negative 1, 0, 0, and 1, 1. N equals 1, of course, is just straight. This red one all the way straight through. This purple one here coming up, and then concave down, increasing. It goes through the origin with an inflection point. Then it goes back up, increasing concave up there. And this n equals negative, or n equals 19 thirds, very similar. That's the maroon one here. But all of these have this origin symmetry, first and third quadrants. Now what if you have a even over an odd? P is even and Q is odd. So notice what happens. Again, we know the first quadrant. We know what happens there. So what happens when n is negative? Well, a negative to an even power is going to be positive, and then you turn around and take a odd root of that, it'll still be positive. And so you got a negative input gives you positive output. For example, negative 1 input gives you positive 1 output. So they all go through negative 1, 1 and 1, 1 with these conditions. Okay? And so that's going to be quadrant 1 and 2. And it turns out that the second quadrant is a mirror image of the first quadrant, so that is what we call y-axis symmetry. And so you see several examples, different shapes that we could get in the first quadrant, but they're all just flipped over to get the second quadrant. So a negative exponent would be like this red one here, n equals negative 2. You can see that. We knew that what the first quadrant was. We talked about that already. Flip it over the axis and get the other quadrant here for second quadrant. N equals 0 straight across in this quadrant, flipped over straight across here, but remember it has a hole in the graph. Okay, you got increasing concave down in the first quadrant for when the power is 2/3. We flip it over, we get decreasing concave down in the second quadrant, and we get a minimum there. Okay, so many of these, all these that go through 0, 0, the ones with positive powers have a minimum there. If we have powers 4/3, 2, or 4, all those are powers bigger than 1, so notice that they're concave up the entire way. 4/3 is getting close to 1, so it's starting to look kind of like it's straight, but not really. It's really concave up all the way. Now what if we have an odd over an even? If we have an odd over an even, again, we know it's first quadrant. What do we do about the negatives? Well, a negative to an odd power is negative, but then when we take an even root of a negative, we get a non-real number. Now, for our purposes here at graphing, we only want to graph things when it's real inputs, real outputs. So for our purposes, an even root of a negative is undefined here. So these functions are undefined when x is negative, and so they're quadrant 1 only. And they all go through 1, 1, of course. And these don't have any symmetry to them. They're only just the first quadrant. And again, I've given some examples. N is negative 1/2. That's the red one there, with the, notice the vertical and horizontal asymptotes. N equals negative 1/16. That's also got vertical and horizontal asymptotes. So those are both decreasing concave up in the first quadrant, and they only have the first quadrant. N equals 1/2. That's the square root function. That's going to be increasing concave down. 3/4 power, that's also increasing concave down. 11/8 is for the power would be increasing concave up. Now it also turns out if the power is irrational, where we can't put it in a fraction form, then we're only going to define those for first quadrant also. So x to the pi power is this maroon one you see here graph that's increasing concave up. So here's a summary of the quadrants in symmetry. If n is irrational, or it's a rational number with an odd numerator over an even denominator, it's in quadrant 1 only, and it has no symmetry. Notice the domain will be 0 to infinity. It'll include the 0 if it's a positive power, and it won't include 0 if it's a negative power. And the range and the domain are actually the same. Okay? If you have a rational power, P over Q, where P is even and Q is odd, so even on top, odd on the bottom, that's going to be quadrants 1 and 2. And the domain is going to be all reals, but the range is just going to be from 0 up. If it's so it's all reals, and it's going to include 0, all reals for the domain, and 0 up including 0 for the range if we've got a positive power. If you've got a negative power, you throw out 0 in both the range and the domain. So the domain is all reals except for 0, and the range is 0 to infinity, not including 0, just the positives. If you've got the power that's rational power where it's odd over odd, then you've got quadrants 1 and 3. And if the power is positive, then the domain and range are both all reals. Everything's included there. If of course, if the power is negative, we throw out 0 out of the domain and the range, but it's everything else. And these have origin symmetry. So we end up with a total of 11 different possible graph shapes when you put these things together. And here they are. So notice if the power is greater than 1, the first quadrant's increasing concave up, so all those in the first row of graphs there are that way. N equals 1 is a very specific graph, y equals x. That's the only one that's a straight line. Okay, increasing straight line there, slope of 1. If the power is between 0 and 1 in the first quadrant, you've got increasing but concave down. That's the next row. N equals 0 is a very specific one. That's a graph that is a horizontal line with a hole in it at 0, 1. It's the line y equals 1 with a hole in it at 0, 1. And if n is less than 0, we're talking about one that has vertical and horizontal asymptotes of the x and y axis. In the first quadrant, it's decreasing but concave up. Okay? Now, if it's irrational power or power where it's a fraction with an even denominator, then it's quadrant 1 only. So this first column of graphs right here are only just quadrant 1. So notice all of these, well, these first two here have an endpoint, which is a minimum at 0, 0 and go up. This one doesn't have a minimum or maximum here, because it goes down 2 but not including 0, so there is no real minimum, and it goes up towards infinity, so there's no maximum either. This one, these two here, where we have quadrant 1 and 2, where we got an even over an odd power, they have a minimum global at 0, 0. But when the power is bigger than 1, it's increasing concave up in the first quadrant. Flip it over, so it's decreasing concave up there. So it's concave up everywhere, but has a minimum. If the power is between 0 and 1, we're increasing concave down the first quadrant. Flip it over, we've got this decreasing concave down, and then it comes to a minimum still at 0, 0. This one, horizontal line, n equals 0, has the hole in the graph at 0, 1. And this one down here, when a power is less than 0, but even over odd, is first and second quadrant. First quadrant is decreasing concave up. Second quadrant is increasing concave up, and they both quadrants have an asymptote of the x-axis and y-axis. Over here in the last column, all of these have origin symmetry. The middle column, all of them had y-axis symmetry. In the first one up here, where a power is bigger than 1 and odd over odd, that's going to be increasing concave up in the first quadrant, rotated around to get the third quadrant, which is increasing concave down. So we have an inflection point, a place where it changes concavity at the origin. The next one is linear, y equals x. The next one here, like maybe a cube root function, for example, is one where it's an odd over odd, but the whole power is less than 1, or between 0 and 1. And so in the first quadrant it's still increasing because of positive power, but this time it's increasing concave down. Rotate around to the third quadrant, you got increasing concave up, and again we have an inflection point at the origin. And the final one down here in the lower right corner is where we have a negative power where it's odd over odd. And again, as all the negative powers in the first quadrant, you just have decreasing concave up, asymptotes of the x and y axes. This time we rotate around, we're decreasing concave down in the third quadrant, again with the same asymptotes. So these are the possible graph shapes that you can get. Of course, two of these are very specific, y equals x to the 0, but all the others are families or classes of them. So now we've looked at every possible power that we could come up with for a power function, and we know what the graph shape should look like. We get the symmetry based on thinking of it as a fraction and whether it's even and odd, and look at the different 3 cases there, or if it's an irrational number. And then we have the 5 cases coming down the side based on the size of the n. Put those together, we get a total of actually 11 possible things that you see here. These grayed out don't actually happen because n equals 0 and n equals 1 are very specific ones. So after completing this section, especially after you've done the inquiry-based project, the minds-on activity, and this video, you should be able to describe the behavior graphs of a power function in the first quadrant based on an examination of the size of the power. You can then talk about things like domain, range, which quadrants are present, and what symmetry the graph has of a power function based on examination of the power, thinking like even and odd of the fraction pair. And understand the meaning of the following graph characteristics and when they apply to power functions based on the value of the power n. And so we did some properties of exponents that helped us understand what was going on here. We talked about domain and range. We talked about increasing, decreasing, and constant. Relative extrema, specifically minima. Endpoints. We talked about concavity, concave up, concave down, linear. And also inflection points. We talked about continuity. Okay, continuity, let's talk about that just a second. Continuity means it's one connected piece. So this first one, the upper left, all of them in this first row are continuous. So is this one here. All in the second row are continuous. But these down here where the power is 0 or negative are discontinuous. They're in two pieces. So this one here at n equals 0 is two horizontal line pieces, but separated with a hole. And the others are separated by a vertical asymptote of the y-axis. So in either case, all of these four down at the bottom, the y-axis sort of divides it into two parts. There's the part to the left of the y-axis, the part to the right of the y-axis, and there is no graph on the y-axis. There's either a vertical asymptote there when the n is negative, or there's a hole in the graph there when n is 0. Okay, so those are called discontinuities. And there were two kinds. There was the hole in the graph, and then there was the vertical asymptote. You also had the horizontal asymptote. Now an asymptote is a line that the graph approaches. So we had the asymptotes when we had the negative power, and so it was getting closer and closer. The graph is getting closer and closer and closer to that horizontal or vertical line, depending on which part of the graph you're talking about. But in this case, it never quite actually touches that. And then we talked about symmetry. Y-axis symmetry is a reflective symmetry, and origin symmetry is a rotational symmetry. And so now we've been able to take this really simple class of functions, just y equals x to some power, but depending on the different powers, we had 11 different shapes that we had there, and by looking at all those different shapes, we had some very interesting characteristics of graphs. In fact, pretty much any interesting graph characteristic that we might want to study this semester, they all showed up here in one or more of these particular graphs.